Welcome back to Valiant PE. Today's topic, linear versus nonlinear FEA. Let's go. Okay, guys, on this exam, FEA is going to be a qualitative topic. We are not going to be solving any quantitative problems to get discrete values. We're going to have qualitative. So that means we need to know our theory really well. Anytime we have a theoretical topic, we have to know a lot about it because they can ask anything about it. Now, we don't have to be an expert in it, but we at least need to be exposed to it. So, in the machine design world, there are two ways you could do a structural FEA. And we're going to stay in the structural realm because thinking from a machine design standpoint, we don't really care too much about vibrations or thermal at this point. We're going to just think about deflection and stress. So there are two types of FEA we can do, linear and nonlinear, and I'll explain what they are. The first thing we need to know is that linear FEA is the place we're going to go to, is the method we're going to go to if we have simple and fast analyses to run. In the machine design world, we have a lot of machine components that are very simple and probably are not intricate and are probably subjected to loads that are going to cause stress below yield. So we're going to reach for the linear tool first. There are two big assumptions about linear structural FEA. The first is that our material behaves linearly. What do I mean by that? Let's draw stress strain curve for steel. Something like that. Not perfect, but something like that. In our linear elastic region, the slope of that area is Young's modulus. Okay. Linear material behavior means that the software is assuming that this portion continues on forever. So our stress strain curve stays linear forever. Linear forever. Now, that means that any strain I get, I'm going to get a corresponding stress. What's the downside of this? Well, no plastic deformation is accounted for. If I get a strain or a stress that's over my yield stress, well, the software didn't account for plastic deformation and my stiffness would change. And that's very, very key. No plastic deformation is accounted for. This may not be a huge deal if the component that we are designing needs to stay below our yield stress. But you need to know that for any given strain, I get a stress. This is the formula. Very simple. Stress is Young's modulus times strain. That also means if we run an analysis and we get a stress in a structure that's over our yield stress, that means that value is meaningless. Stresses over yield are meaningless. Meaningless. So if I get a stress up here that's above my yield stress, I know it's inaccurate, okay? But this is not, though it has shortcomings, it's not a bad choice if the component we're looking at is simple. And if we're going to stay below yield, this is a fast choice for us to go to. So we're going to save on computational time. That's a big deal. The second big assumption is that our geometry behaves linearly. What do I mean by that? Let's say I've got a column, and it's a slender column. There is a load that I can apply, a fixed base here. There's a load that I can apply. It's going to be my critical buckling load. It's going to cause this column to buckle. And it is going to be less than the force that's required to yield this bar axially. So linear FEA assumes, nope, we don't have any buckling. Buckling's not predicted. It's just going to keep on deforming. So if we suspect that our machine component that we're analyzing may have a buckling risk, linear FEA is not the tool to reach for. The second thing is anytime we have a membrane, like a membrane structure, think of like a thin sheet applied to over a lattice or something. A good example of this is, say, your car door. you can like close it with your hip and bump it, and you can even feel it kind of pop in and pop out. Or if you've got an old baking sheet, you can kind of pop it or twist it, and you can feel it kind of catch and stick. That behavior below yield is not going to be accounted for in linear FEA. So then why would we ever choose linear? Well, okay, if the machine component that we're going to be looking at remains below our yield stress, this is the way to go. If we're going to stay in this region here, and we're just going to go up and down the linear elastic portion of our curve, linear FEA all day long. Second thing is that the setup is really simple. If the component that we're looking at can be isolated and we can just look at one component, this is the tool to reach for. If we've got an assembly, or we've got components contacting each other or sliding against each other, this is not the right, linear is not the right tool to reach for. But it's very good at simple setups and components that are going to stay below yield. When then would we reach for nonlinear? Well, obviously anytime these criteria is not met, but the first thing we really need to know about nonlinear is that the runtime is going to go up. This is the big advantage that linear has over nonlinear. The runtime gets a lot bigger when you have nonlinear FEA, especially if you've got contacts or assemblies of big components. Anytime we want to predict plastic behavior, we're going to need to use nonlinear. And these basically just refer to settings in the software of like how you're going to do a run. We don't need to get into that for the purposes of this exam, but the last thing we need to know is if you got a contact type situation, or you've got a friction situation, you got sliding situation, assemblies, these are times we're going to reach for the nonlinear tool. That's it, guys. I don't think we really need to go too much deeper here. Again, this is a qualitative topic. If we understand our stress strain curve and some of the assumptions the software might make, that's all we really need to know. If we're staying below yield, we're going to go with linear. There's a lot of stuff on the internet out there about FEA, all types. I think just reading, my suggestion is just to read. Anytime we have a qualitative topic, the more we can just be exposed to, the better. But with this info, guys, and the other FEA video I've done, I'll link it in the description. I think that's all we need to know about FEA for this exam, and we can handle anything that they throw at us. Remember, you don't have to be a genius to pass this exam. Thanks for watching.